To start the demonstration, open MSC Apex. We will first change our units to the English system. To do this, we go to Options, Application Settings, click on Units and Parameters, then click on the Unit Systems button. In the table that appears, we pick inch, slinch, seconds, pound force as our system of consistent units. After highlighting it, we click OK. Now let's create a 12 by 8 rectangular surface. We do this by clicking on the Geometry Create icon from the Tool palette. Click the 2-point rectangle sketching tool to draw the surface. On the screen, pick the XY plane, which if you take a look at the interactive triad in the lower left corner of the screen, is the bottom plane. This is where we will create the surface. Once the plane is picked, zoom out, then click anywhere on the grid to begin drawing a rectangle. Then click again to complete it. To get the exact dimensions, click on an edge, type in the value, and press Enter. We do this for both dimensions. Next, exit the sketching tool by clicking the Close icon. Now let's define the material for the part. We click on the Material icon, click on Create Material, change the name to aluminum. Since we are running a modal analysis, we must enter density, which is expressed here in slinch over inches cubed. Then we enter the elastic modulus in PSI and Poisson's ratio. Once we finished entering the material data, click on Assign Material, then click on the surface to assign the material to it. Click on the Close icon. We now have to define the thickness of the surface. We do this in sections. Clicking on the Sections icon brings up the form in which we will enter the thickness. Here we accept the default name of Section 1, and then enter the thickness value of 0.125 in the thickness box. Once we've done this, click on Assign Section, and then click on the surface to assign the section property to it. Click on the Close icon. Next, we want to apply the shell behavior properties, which will allow us to specify whether we want our 2D finite element model to support membrane, bending, and transverse shear loads. In this case, we click Create Behavior and accept the defaults, which will allow the model to support all of the load types. We click on Assign Behavior and then click on the surface to assign these behaviors to the model. Next, we will create the pinned constraints on the 4 edges of the surface. We click on the Loads and Constraints icon, click on Fixed Constraint, then enter Pinned under the name. We then uncheck all the rotational constraints, leaving only the translational constraints checked. Then we apply the constraints to the edges of the surface. Finally, we apply the mesh by clicking the meshing icon and selecting Surface Mesh under Meshing Tools. For mesh size, we enter 0.4 inches and we click on the surface to mesh it. You can see that this gives us a fine enough mesh to be able to represent the modal deflections smoothly. Click the Close icon. The model is now ready for analysis. We then go to the Model tab, right-click on Part 1, and select Set Analysis Context. MSC Apex will report that loads are missing. This is because the simulation type defaults to a static analysis. We need to change the simulation type to normal modes. Now MSC Apex will report that no offenses are identified and that the current analysis context is ready for submission to the solver. Then we proceed to run the analysis by clicking the yellow Running Man. Now that the analysis has completed, click on the Post-Process icon and double-click Mode Scenario Part 1. We can see that the analysis has returned 10 mode shapes and the frequencies at which they occur. The first mode shape is at 263 Hz, which compares to the theoretical value of 265. Now let's click on the fringe icon to color code the model based on translational displacement. We also click on the Shaded with Edges render style icon to have a continuous display. Finally, we click on the Play Forward button to animate the mode shape. To get a better view of the deformation, rotate the model into an isometric view by clicking on the white sphere at the center of the interactive triad in the lower left corner of the screen, or by pressing both mouse buttons simultaneously and holding. To get an even better view, we hold down the middle mouse button and move the mouse. Here we see the first mode shape at 263 Hz. The second mode shape at 505 Hz looks like this. We can step through the other mode shapes by clicking on the bars as shown. Note that the displacements are normalized. Their relative value to each other is accurate, but their magnitudes are not absolute. This concludes this demonstration.